had completed 2 problems from the tutorial on memory systems or cache memory. 2 more remaining. So let us look at the third one. Now, a cache can hold 3 blocks of data and is fully associative. So we have a fully associative cache memory. Consider a request sequence as follows: 1, 2, 1, 2, 3, 3, 4, etc., 5. Draw a diagram that identifies the block to be replaced whenever a miss occurs, assuming that an optimal replacement algorithm is being used. So here we have a cache which can hold 3 blocks of data. Okay, and we have to see what is the sequence or what is a block to be replaced whenever there is a miss. And let's get started with drawing a few blocks like this. Okay, so on and so forth. So we can see that the first time the block being requested is block number 1, and our cache can hold only a total of 3 blocks. So what will be the situation when the system is powered on? Is there anything in the cache? So is it possible for you to get a match with the address sent by the processor? Well, it's possible, because when you power it on, it could be some random data which could correspond to, if you are lucky or unlucky, the address issued by the processor. And that's why we have a valid bit for each block, and the valid bit is cleared on power on. So there is some additional circuitry which will detect a power on event and clear all these valid bits. Okay, so that the first time access to any block will be treated as a miss for sure. So the first time you are accessing, block number 1 is being accessed. So is it a miss? Yes, it is, right? Because there is nothing valid in the cache. So you can put 1 anywhere. Since it is a fully associative memory, any block can go to any location in the cache, right? Any main memory block can go to any block in the cache. So you can write the 1 anywhere and it is still correct. So just write anywhere. And this sort of a miss is what we call a compulsory miss, because block number 1 is being accessed for the very first time, right? Irrespective of your cache design, it's going to be a miss, it has to be a miss. So we call it a compulsory miss. Then 2 is being accessed. So 1 is already there. Now 2 is being accessed, which is also a miss. Okay, so when there is a cache miss, the cache controller will initiate a read from the main memory, and the corresponding block will be placed in the cache, and then it will be forwarded to the processor, right? So anyway, the cache will be updated. So the 2 can go anywhere, but let's follow the order. And then 1 is requested again. So originally 1 and 2 are there in the cache. So 1 is being accessed. So now you have a hit, right? The previous 2 were misses, and now since 1 is being accessed, it's a hit. Now next, 2 is being accessed. So 1, 2, and you will have a hit again, right? Because 2 is already there. The next block to be accessed is 3, and 3 obviously is not there in the cache, so we will have a cache miss. So originally we had 1 and 2, and now 3 is accessed, so it was not there, so it's a miss. So the unused location of the cache will be used to hold the block number 3. And then we have a request for 3 again, and this time we get lucky because it's already there, so you have a hit. Next, 4 is being accessed. So again we can see that the current contents are 1, 2, 3, and since 4 is accessed, we don't have it, so it's a miss, right? 4 is not there anywhere in the cache, so it's a cache miss. So which one will be replaced? There are 3 replacement strategies that we are covering in this module. In fact, there are a lot more. So 3 simple replacement strategies are least recently used, first in, first out, and optimal. In first in, first out, the very first block or the oldest block in the cache is a candidate to be replaced in FIFO, first in, first out. Least recently used, the block which was not used for the longest period of time is a one to be kicked out. So even if it came to the cache much earlier, if it was recently used, it will still be kept. Okay, and the block which was not used for the longest period of time is the first one to be kicked out. Okay, so LRU. And optimal is an algorithm which is not realizable in practice, not in real time, but optimal algorithm is still used to benchmark the performance of other algorithms, because optimal algorithm is the best possible case, but it cannot be achieved in real time because an optimal algorithm requires prediction of future, right? And such a technology doesn't exist yet, and it probably will never. So we can't really implement optimal algorithm. Now, what does an optimal algorithm do? FIFO and LRU are both based on history. FIFO bases it on when was it brought into the cache, and LRU bases it on when was it last used. Whereas optimal algorithm will look forward instead of looking at history. Okay, when is it going to be used? So the block which is not needed in the near future is the one that will be replaced. Okay, so here the question is about optimal. So let's look at what optimal strategy would be. So now, since 4 is to be brought into the cache, either 1, 2, or 3 should be kicked out. The 3 occupants of the cache right now are 1, 2, 3, right? So look forward and see which one is not required in the future or not required in the near future. 1 is needed in the future, 2 is needed in the future. So our candidate will be 3. So 3 will be kicked out and will be replaced with 4. And what happens when 3 is evicted from the cache? If a write back scheme is used, you have to check for the dirty flag. If the dirty flag is set, then block number 3 has to be returned back into the main memory. So it should trigger a write operation. Whereas in a write through scheme, you don't have to worry about block 3 at all, because any change that happened to block 3 would have been instantaneously updated in the main memory as well, right? So there is no need for any dirty flag. There is no need to write back the whole block. Okay, but it's not within the scope of the question. I was just mentioning it. So now 4 is in, 3 is out. And let's see which one is the next one that is requested. The next request is for block number 1, right? And block number 1 is already present, so you have a hit. And now give me a sec. The next request is for block number 5. Is block number 5 present in the cache? No, it's not. So 5 is requested. 5 is not present anywhere in the cache. So you have a miss. So by the way, the requested blocks are 1, 2, 1, 2, 3, 3, 4, 1, 5. Okay. So now we have a miss, and this is also a compulsory miss. And which one will it replace? 1, 2, or 4? You can look forward and you can see 2, 4, 2, 5 are required. So it's not going to be 2 and 4. So the block to be replaced is 1. And now 5 will replace 1. And next block that is requested is 2. And 2 is already present, so you have a hit, right? And the next block to be requested is 4 and 4 is also present, so you have a hit. And the next block to be requested is 2 again, and 2 is there, so you have a hit. And the last block to be requested is 5, and 5 is also there, so you have a hit. Okay, so how many misses are there in total? 1, 2, 3, 4, 5. 5 misses, right? And okay, all the 5 misses here are what we essentially call compulsory misses, because it's required for the first time, so you will have a miss. Now let us see what would have happened if we had used FIFO, first in first out. Then where will be a change in this case? Where will there be a change? So let's see. So here is where you had the first miss because the capacity was exceeded, right? So here, which one will FIFO replace? Here FIFO would have replaced 1, right? So 4 would be coming in place of 1, because 1 is the oldest one in the cache, right? We are looking at FIFO. So earlier for optimal we had 5 misses, and let us see how many misses we will have for FIFO. So here 4, and then here it would have been a miss, right? It would be a miss because this was 4 and this was 3. And which one will be replaced? 2 will be replaced, because 2 among the 3 blocks in the cache, like 4, 2, 3, 2 is the oldest one to come into the cache. So 2 will be replaced with 1. So the situation would be 4, 1, 3, and this would be a miss. And then 5 comes in, that will also be a miss, and 5 will replace 3, right? 3 is the oldest in the cache. So 3 will be replaced with 5. So originally it was supposed to be 3, and now it will be 5. So the situation would be 4, 1, 5. So this is 4 and this is 1 and 5, right? And now 2 is requested. This will also be a miss, because the contents are currently 4, 1, 5. So among 4, 1 and 5, which is the oldest? Yeah, 4. So now 4 will replace, 2 will replace 4. So 2 comes in here, 1 will be here, 5 here, right? And now 4 is requested, which will also be a miss. So you can see that in this particular case, your FIFO replacement scheme does a pretty terrible job, right? It is replacing something which is required in near future, but the policy is that you don't look into the future, you look at the past. Okay, so among 2, 1, 5, which one should be replaced? So 5, 2 should be kept. Yeah, 4. Yeah, so it's 2, 4, 5. And then next, 2 is requested. So finally we have a hit, right? So it will remain 2, 4, 5. And then 5 is requested. We have a hit again. So you will have 1, 2, 3, 4, 5, 6, 7, 8 misses. So here FIFO will give you 8 misses as opposed to 5 misses by your optimal algorithm. Okay, you can also try with LRU. LRU is very simple. Whenever there is a decision to be made, you look at which one was recently accessed, right? Now there are a lot of other replacement algorithms that are used in practice, and one of those very frequently used one is a frequency based approach. Okay, instead of looking at when was it used, or instead of looking at when it came in, you look at how frequently it was accessed in the past. So every time a block is used, you increase a certain counter associated with that block, and the block with the lowest count will be the one which will be replaced. Okay, because that was the one which was least frequently used. Okay, and then there are combinations of these, like which looks at multiple factors before taking a decision. But still, none of these algorithms can be very complicated because all these decisions typically have to be done in less than 10 clock cycles. Okay, maybe 3, 4, 5 clock cycles. Because cache is supposed to be something which is very fast, right? So you can't really run any complicated algorithm to do more complicated analysis to make the decision on which one to replace. Okay, so none of these algorithms can be very complicated. It's all fairly simple, easy to understand as well. You can read the Wikipedia article on replacement algorithms, and they already list a number of different algorithms. Okay, like I said, just by looking at the title, you will already get an idea of what the algorithm is. No complications there. Now that completes the third question. Let's look at the fourth question. Which mapping strategy is used in level 1 cache by latest processors from Intel? Of course, this kind of questions won't be examinable, but just to have some awareness of what's going on, what is the state of the art, we can have a look at the question. To answer these sort of questions, the best place for you is this website called WikiChip. Okay. It's a very nice website which contains a lot of information about recent as well as historical processes. Okay, a wealth of information you probably won't find anywhere else. So if you look at the latest architecture from Intel, it's Coffee Lake. So you can read up and get some information about the Coffee Lake processor in this WikiChip. So they give a lot of details about the exact transistor sizes and the various changes from the previous generation, which is called KB Lake, and also an overview of the chip, like how many cores are there and how they are arranged, and even the microarchitecture. So this is the microarchitecture of the Coffee Lake processor, how exactly it looks from inside. So in fact, okay, it's a bit hard to understand, but you will still find it a bit familiar, some of the things here and there. Yeah, so it still has a pipeline, but it's not really a linear pipeline like the pipeline that we had seen. But yeah, you can read up and have a look. And again, if you take CG2028, you will get a better idea of all these stuff. Now, the memory hierarchy is also clearly explained here. So you can see that there is an L0 cache, which is what we call a micro operation cache, which is not a conventional cache, which is only there for instructions. So, Intel processors are CISC processors, right? I had mentioned earlier about CISC versus RISC. So what they do is take this complicated instructions and split them into simpler instructions. So even though it looks CISC from outside, it is somewhat RISC internally. So the complicated instructions which the programmer or the compiler generates is translated on the fly to a bunch of simpler instructions, which the programmer can't see. And these simpler instructions are what we call micro operations. So this decoding, after it is done, the decoded simpler instructions or micro operations are stored in a small cache. Okay, so that if the instruction that is required is already present in the micro op cache, you don't have to do the splitting up or the translation into simpler instructions again. Okay, which will allow you to save time as well as power. So that's what we call the micro operation cache, but it's not a cache in the conventional sense of the caches that we have dealt with. So the real cache starts from L1. So it goes all the way from L1 to L3. So you can see the L1 cache is 32 KB and it is 8-way set associative. You can see there are 64 sets and 64 byte line size. This line size is nothing but block size, because block is also called a cache line. So line size is the same as block size. Okay, and you can see more information here. The data cache, so you can see there is a separate instruction cache and data cache. So the data cache is also 32 KB, 8-way set associative, which means it's 64 sets and 64 bytes per block. And L2 cache you can see is unified. Unified means there is no separate instruction or data cache. It's one single cache. 256 KB and it's 4-way set associative. And then L3 cache, 2 MB per core. So in a dual core processor, it will be 4 MB. In a quad core processor, it will be 8 MB shared across cores. So even though it's 2 MB per core, the entire cache is accessible to all the cores. So for example, if you have a 2-core processor, you are looking at 4 KB, right? Sorry, 4 MB of level 3 cache. This entire 4 MB can be accessed by both the processes. That's the idea. Whereas L1 and L2 cache are private to each core, but it is shared by the 2 threads within the same core. And I think I had mentioned it in the class day before yesterday that there is this technique called hardware multi-threading or simultaneous multi-threading. Intel calls it hyper-threading, where 2 threads run on the same core because the operating system sees it as 2 separate cores, even though in reality there is only 1 core. So the scheduling between the 2 cores is actually done by hardware, not by the operating system. Okay, so that's the idea of multi-threading. So here the lower level caches are private to each core but accessible to both the threads within the core. That's the idea. Then there is L4 cache, also called a side cache, which is either 64 MB or 128 MB, which is available only on certain higher end versions which have Iris Pro GPUs, okay, like Core i7 versions. Okay, so that completes this tutorial. Now for the last tutorial, I had already covered question number 1 in the class, but I will just quickly go through it once again. But I really do not have the bandwidth to give a lecture, a recap of the lecture. So I'll just go more or less straight to the tutorial. So from now onwards, you should be a bit more aware of what is going on in the market, what are the trends, etc., etc. Because as computer engineers, you can't simply be users anymore, right? You should be aware of what is out there, how the technology is changing, etc., etc. Because eventually, when you enter the industry, you might be required to make a choice regarding which processor to use for a particular computer system. And you should have some awareness of how the technology has progressed, right? Some history, some knowledge of the current trends, etc., etc. Because as I say, those who do not know the history are doomed to repeat the mistakes of the past. Okay, now this chapter, last chapter is about pipelining. Probably the toughest chapter to understand or fully appreciate, though it's not too difficult to get some appreciation. So we had seen that in the single cycle processor, you had your load instruction, which was taking the maximum amount of time. And here I have given some rough numbers to give you an idea of how much of a performance degradation your processor encounters because it has to accommodate load instruction. Okay, because of load instruction, every other instruction takes more time than it should, because your clock period should be big enough to accommodate the worst case execution, which is your load instruction. So for other instructions, you can see that some part of the clock cycle is wasted. So you have thrown in money to buy the hardware, but your hardware is remaining wasted or unutilized for a good part of the clock cycle, right? That is almost like renting a room in Marina Bay Sands and not occupying it. So how do we make it faster? And that's where the idea of pipelining comes in. So instead of executing one instruction in one clock cycle, you split up one instruction into a certain number of stages, and only one stage is completed in one clock cycle. So here we have the example of a 5-stage pipeline, but you are not limited to using 5-stage pipelines. As a designer, you can choose. There are of course trade-offs associated. Most modern processors have about 15 pipeline stages, more like 15 to 20. But of course, lower end processors will have less number of pipeline stages. If you increase the pipeline stages, you generally get improvement in performance, but it will also increase the power consumption, cost, etc., etc. And the amount of improvement in performance that you get with each additional pipeline stages diminishes. So when you go from a 3-stage pipeline to 5-stage pipeline, you will get a lot of improvement, but you won't get a proportionate improvement if you go from, let's say, 8 pipeline stages to 10 pipeline stages. Okay, even though it's an improvement by 2, the improvement will not, the performance improvement is not proportional. Now, what is the number of pipeline stages I am talking about? It's a number of stages to which one instruction execution is broken up into. So for a 5-stage pipeline, your instruction execution is broken up into 5 pieces: instruction fetch, decode, execute, memory access, and write back. Now, instead of doing it all in one cycle, which was the case for a single cycle processor, we do only part of it, only one stage in a cycle. So now your clock frequency can be faster. But does it reduce the time taken for one single instruction to complete? No, it doesn't. It still has to go through all the stages. So now your clock cycle is faster, or clock period is faster. What did I say? Clock frequency is faster, that is clock period is smaller, but it will take larger number of clocks to complete the instruction. So in ideal case, your clock frequency can be 5 times that of the single cycle processor, but it will take 5 cycles for an instruction to complete. So the time taken for an instruction to complete does not reduce. Then why do we do pipelining? Well, the idea is that when this LDR instruction, or any instruction that comes in first, when it goes from fetch to decode stage, the next instruction can go from not being existing or not existing inside the processor to the fetch stage. So you can see that in cycle 2, not here. So the next instruction will be started in cycle 2, and it runs all the way until cycle 6. So the first instruction starts in cycle 1, completes at the end of cycle 5. The second instruction starts at cycle 2 and ends in cycle 6. So you can see that there is an overlap of instruction execution, which is okay because different instructions will be at different stages of execution. I have it here. Different instructions will be at different stages of execution at any given time. Okay. So while this LDR instruction is in execute stage, the following instruction will be in decode stage, the following one will be in fetch stage. So the advantage of that is, at the end of cycle 5, first instruction completes. At the end of cycle 6, the second instruction completes, and so on and so forth. So even though the time taken for one instruction does not reduce, the number of instructions that you can complete in a given time increases. Because now one instruction completes every cycle, but your cycle time is smaller, which means the number of instructions that complete in a given time has now increased tremendously. So in the ideal case, you can see that one instruction completes every cycle, but your cycle time is 1/5, which means your throughput increases 5 times. So that's the whole idea of pipelining. Now, how do we convert a single cycle processor into a pipeline processor? Well, this is your single cycle processor. So this part is your fetch, which is about reading the instruction memory and getting the instruction. This part is what we call decode, which has to do with decoding the instruction as well as reading the register file. And this part is what we call execute, which is to perform the ALE operation, either to do a computation or to calculate the effective address depending on instruction. This is your data memory access, and this part is what we call write back. Eventually the result is written back into the register files, right? So write back. So the way we do it is use registers to separate the stages. because your clock cycle time is limited by critical path, right? Critical path is the time taken for an instruction or any signal to propagate from one register to the next register. So by introducing more registers in between, you are reducing the critical path. And it is also required because when an instruction moves from one stage to next stage, all the information regarding this instruction should be latched into this register so that it will be available for the next stage. So whenever information or whenever a signal crosses a clock boundary, so here in this clock, let's say the instruction is here. When it crosses a clock boundary, here it has to be stored in a register. You cannot have an information crossing a clock boundary without it being stored somewhere. That's the idea. So now you need to introduce 4 registers like this to separate the single stage into 5 different stages. Okay, like you require 4 cuts to cut something into 5 pieces, right? Like a bread loaf. So same idea here. So this is your fetch stage, decode stage, execute stage, memory, and write back stage. And you can see that in the write back stage, the write back stage is the light blue color here. You can see things flowing back like this. Because in the write back stage, you are writing it back to registers. Okay, either the program counter, which is a case for a branch instruction, or a register file, which is a case for a load instruction or a DP instruction, right? And pipelining is a very simple and very easy thing to do if data flows only in one direction. Okay, so if it proceeds in the same direction, like in an assembly line, it's very easy. But whenever the data goes against the traffic, you will have trouble. So here you can see the result is written back into a register file, or in case of branch instructions, the result is written back into the PC. The result is essentially the BTA, right? And this traveling back causes a lot of problems. This data traveling back into the register file causes something called data hazards. And data traveling back into the program counter causes control hazards. So as I mentioned in the class, the basic concept of pipelining is simple, but the devil is in the details, as is with most things. Okay, so we have to be mindful of what happens when the data travels back. The issue really happens when, let's say, you have instructions like this. So this is what we call an abstract pipeline diagram, which allows us to visualize the pipeline very easily. And here you can see that R1 is written to by this add instruction, but this R1 is required for the next instructions, next 3 instructions. So the problem with this is that this instruction writes to the register file, so the new R1 value is committed only at the end of cycle 5. So this is a point in time where R1 is updated. But this instruction will read R1 in its second cycle, which is a third cycle of execution of the processor, because this instruction starts 1 cycle later, right? So this is a point in time at which you need the data. This is a time at which the updated data is available. And this R1 value should indeed be the R1 created by the previous instruction, right? That's how the information flows from one instruction to the next instruction. So now you see, you are trying to access a data which isn't there. And this is what we call a data hazard, also called a row hazard, read after write hazard, because you are supposed to read only after you write. If you try to do otherwise, you will have this row hazard. And row hazard can manifest or can exist between a particular instruction and any instruction which is 3 instructions from there. So this is the next instruction, the second instruction from there, and the third one. If there is an instruction here which uses R1, you wouldn't have a problem, because you see this instruction starts in cycle 5 and it will require the register value only in cycle 6, which is its cycle 2. Because reading of registers happen in the second stage, right? So the second stage comes only in cycle 6, and by the time the data is already returned. So the moral of the story here is that if an instruction writes to a register which is used by or which is a source for any of the 3 instructions that follows it, you have trouble. Got it? The 4th instruction onwards is okay for you. So if you want to be absolutely safe, you have to make sure that the following 3 instructions do not change anything. They are essentially useless instructions. So that's what we call NOPs, no operations. So in order to ensure the correctness of your program execution, the following 3 instructions have to be NOPs if there is a potential of a data hazard. So if instead of R1, if it was using some other registers, like for example, if it was all, let's say R11, then no problem at all, because this instruction writes to R1, but these instructions do not use R1. So the value of R1 being changed has no effect on the following instructions. So it's okay. But if there is a data hazard, which is also called a true data dependency or a row hazard, then we have to ensure that instead of having these 3 instructions, we insert 3 NOPs here to space the 2 instructions with dependencies by at least 3 instructions. Okay, so here between these 2, since they have a dependency between them, you insert 3 NOPs, which will ensure that your data integrity is not compromised, your program functionality is not compromised. So that's the idea of data hazards. Now there is another hazard called control hazard, which happens when you have a branch instruction. So let's say you have a branch instruction here. So the branch instruction is supposed to make the program counter change to some other value here. So the branch instruction is supposed to change the program counter value abruptly. So the basic idea of pipelining was that you can start the next instruction before the previous instruction has completed, right? And now this is no longer true for a branch instruction, because if the branch is taken, the next instruction is not your next sequential instruction. And that is what you call a control hazard. A control hazard can be caused by branch instructions, writes to R15, or interrupts, etc. Interrupts can also do the same thing, right? You know what interrupts are, right? When interrupts happens, instead of running your current program or continuing your current program, you will suspend it, go to something called an interrupt service routine, execute it, and then come back. So all these cause control hazards. And in order to make sure that your control hazards do not affect your program correctness, the 4 instructions that follows a branch instruction should be NOPs. And what is the advantage of that? This is a time at which your PC is updated by the branch instruction. And as long as you start your next instruction from the correct PC, it's okay. So you can see here that the instruction fetch for the next instruction should happen only after the PC is written. So in between, the 3 instructions you have should be all no operations. No operation is just a waste instruction, useless instruction like move R0, R0. Okay, which effectively does nothing. Because if instead of this, if it is any other instruction, like for example, let's say R does some instruction. The problem is that this, okay, let's say if this is an R does instruction. The R does instruction will change the processor flags by the end of its execute stage, because the processor flags, NSHCP flags, are in the middle execute stage, right? So before you realize that this instruction was not supposed to be executed, it has already made changes to the processor. And that's not okay, right? Because the instruction was not supposed to be there in the first place. How can it change the state of your processor or computer? And the same issue could happen with, for example, store operation, or any instruction which changes anything can cause issues. even this OR instruction, for example, it will end up changing R9 here, R9 at this point of time. Unless you have a specialized hardware to block it from doing it, once it has entered the pipeline, you don't have a control over it, right? So it will just proceed down the pipeline, changing whatever the instruction is supposed to change, even though the instruction was not supposed to be there in the first place. So the moral of the story is just put 4 NOPs after the branch to solve the problem. And that information is sufficient for us to look at these problems. Okay, I'll go through it a bit fast because I don't have much of a time. I don't want to stretch it to the next week. I had already covered it in the class, so you can just refer to the webcast if you want to. So you have these 6 instructions here, right? And we are supposed to figure out where to insert NOPs to ensure that your program executes correctly. So here you see you have L1 writing to R8. Is R8 used by any other instructions after that? No. So L1 does not have a dependency with any other instruction. Now let us look at L2. L2 writes to R1. Is R1 used by any instructions here? Yes. And if you know that it is used by any other instruction, you have to check whether it is any of the 3 immediately following instructions. Otherwise, you have no problem. The problem happens only if the R1 that is written by L2 is used by any other instruction within the next 3 instructions. And here, unfortunately, yes, we have a problem, right? So we need to ensure that these 2 lines are separated by at least 3 instructions. And what is their current separation? The current separation is only 1. There is only 1 instruction to space the 2. You need 3. So you need to ensure that at least 2 NOPs are inserted. So you have multiple possibilities for that. Either you can insert 2 NOPs here, or you can insert 2 NOPs here, or you can insert 1 NOP each. Doesn't matter where it is inserted, right? As long as they are spaced by 2, you are good to go. Now next, L3 writes to R2. Is it required by any other instruction after that? No, no problem there. Then L4 writes to R3, which is also not required. CMP does not write to any register, but it does write to, does it change anything? Yes, it changes flags, processor flags, but that is okay because your branch instruction will read it only after your CMP has changed it. So for example, here, if you look back at this diagram, you can see that, okay, let's say if the CMP instruction changes a flag at the end of this. So when CMP goes here, the branch which was here comes in here. And the branch instruction reads the flags after the CMP has written. So there is no problem. Okay, as long as you read it after the write is complete, it's okay. So coming back here, so you don't have any problem except there. But L6 has a problem. What is the problem here? L6 gives rise to control hazards because there's a branch, right? So how do you solve the problem whenever there is a branch? Yeah, put 4 NOPs after that. So 4 NOPs. Problem solved. Okay, so fairly easy. In fact, if you don't want to think too much, just think of it this way. Whenever there is a data hazard between 2 instructions, make sure that they are spaced by at least 3. If the spacing is not 3, insert the sufficient number of NOPs to make it 3. And whenever there is a branch, just put 4 NOPs after that. That's a basic idea. Now 2. Can the instructions in the code above be rearranged to reduce the number of cycles required? So can you rearrange the code to reduce the number of cycles? That's the question. So earlier, how many NOPs did you have to insert? 2 NOPs, right? 2 NOPs here and 4 here, a total of 6. So the question is, can you reduce from the 6? Can you? What is the option, alternate option to inserting NOPs? Yeah, you can move independent instructions to fill up the slot instead of NOPs, because NOPs are useless, right? I mean, they ensure program functionality, but they don't do any useful computation. So if you can move any independent instruction forward, then the effect of the instruction will be retained, which means you are doing some useful work while ensuring that the spacing is increased to ensure accuracy of execution when you have 2 instructions with dependencies. So here, between this and this, you need to have spacing of 3. Currently there is only 1. That's why you have to insert 2 NOPs. So can you do any rearrangement to reduce the number of NOPs required? Can you bring down the first line to this spot? Does it change anything? You have to do some checks to make sure that it doesn't change anything. That there are 3 checks essentially that you need to do. First, you ensure that R1 is not a source of the instruction that is coming down. Otherwise, you have a problem, right? You cannot change the order because this R1 is not supposed to be the same as this R1. Okay. The second check is that this does not have any dependency this way. So you have to check on both diagonals. So if R8 was used by the second instruction, then the first instruction cannot be after the second instruction, right? Because the second instruction uses something which was created by the first instruction. The third is ensure that they don't write to the same register. If they do, you cannot change the order because the following instruction should be using the value returned by the second instruction, not the first instruction. Okay, so you check along this diagonal, you check along this diagonal, you check along this lines. And if all the checks are passed, then you can change the order. By the way, there are nicer terms for all these checks, but let's not go into details. One check is something which we already know, right? This is what we call a true data dependency or a row hazard. The other one is what we call an anti-dependency. This is what we call an output dependency. But let's forget it. Okay, but it is very clear that they don't use any of the same registers at all. So absolutely no problem. You can just bring down L1 after L2. Okay, so you can just exchange L1 and L2. Is there any way to fill up the one more gap? Because now the spacing has become 2. Right? Earlier it was 1, but by exchanging L1 and L2, you increase the spacing to 2. But we need one more independent instruction. Is there any independent instruction that you can push up? Yeah, L5 you see. L4 cannot go up because L4 is supposed to be further away from L2, right? So L5 you can see is quite independent because it is making use of R0, which is not used by any of these instructions. So you can easily push this also up. So you can actually exchange L5 and L4. And then you don't need any NOPs anymore. That's the idea. Can you do anything about the NOPs after branch? The question is, can I, let's say, bring L4 all the way down to this? Then you can solve all the problems in one shot except for the 3 NOPs here. Right? Is it possible? Okay, think about it. Okay, in fact, if you push L4 to this position, it's still okay. L4 will still update, and since L4 does not use any register that is modified here or vice versa, it's okay actually. Okay, so you can reduce the number of NOPs to just 3 from the original number of 6. Okay. Now, what is the total number of cycles required for executing the code obtained in Q2 if the branch is not taken? In fact, it doesn't matter whether the branch is taken or not. all the NOPs will still be executed. It is just that it doesn't do anything, right? So the information that the branch is not taken is not very relevant here. Now the number of cycles, what is the total number of instructions executed? You have a total of 6 instructions plus 3 NOPs, total of 9 instructions, right? So for 9 instructions, how many cycles will it take? Anyone? Yeah. How many cycles will it take for 9 instructions to complete? How many cycles will it need to fill the pipeline? If you look at this diagram, you see the first instruction completes only at the end of 5 cycles. The second instruction completes only at the end of 6 cycles. The third instruction completes only at the end of 7 cycles. So how many for 9 instructions? Yeah, 9 plus 4, 13. Yes. Because in the first 4 cycles, nothing completes. At the end of cycle 5, 1 completes. So you essentially need to add 4 to the total number of instructions. So the total is 9 plus 4, 13. Okay. So I guess that completes our stuff. Okay, thank you. I'll have some consultation sessions next week so that you can just walk in and ask me doubts if you have any. So I'll let you know via email.